Hello everyone. My name is Michael Sünkel and I'm a PhD student of computer science at the chair of mobile systems at the University of Bamberg in Germany. First of all, I would like to thank the organizers of PerCom for inviting me here today and giving the opportunity to present our work. Our approach is about resource-aware classification, which we reach via model management and data stream optimization. For a start, I placed an XKCD comic here, and it fits both the topic of the session and the topic of our approach very well. In the comic, you can see that a machine learning task is offloaded to a user, but the machine learning task is a time-critical one, so it doesn't make any sense, of course. We are also offloading or distributing or deploying tasks within a machine learning pipeline, but in a smart way to gain a reduction of resource consumption. The presentation is structured as follows. First of all, I will get into details about our real-world use case, and then I will show the different steps or components of our approach, which are model set mining, decomposition, redundancy elimination, and operator placement optimization. Then I will tell you how we evaluated our approach and how it performs within our real-world use case. And finally, I will conclude the talk. Let's assume that there is farmer Alice, and she owns a dairy cow farm having some dairy cows. She has a lot of work to do, and she also needs to monitor the health condition of her animals manually. She's thinking about how could she get some assistance in health monitoring. She gets aware of an IT company which provides a system which is doing this task. Within this company, there is data scientist Charlie and domain expert Dave, and they collaborate with each other to train models to classify the behavior of cattle. Also within this company, there is IoT engineer Bob. And IoT engineer Bob is now responsible for installing and setting up this system to the dairy cow farm of Alice. So he assembles the sensors and installs the software accordingly. He needs to properly select the models and needs to properly configure the classification pipeline for a smooth and accurate classification. On this slide, you can see a picture which was taken on one of the 3 farms where we have collected our data for our use case. You can see that this dairy cow is wearing a collar, and on this collar there is a sensor box attached to it. This sensor box is containing an inertial motion unit sensor, which consists of an accelerometer, a gyroscope, and a magnetometer. There are some drawbacks in this use case from a computer scientist's perspective. The IoT engineer Bob needs to perform a lot of manual steps in order to set up this classification pipeline properly. He needs to manually select and combine the models retrieved from the model management system. He needs to manually implement the classification pipeline of those models, and he needs to manually place and deploy the classification pipeline to the physical infrastructure. Bob might need to perform those steps over and over again until all the requirements are met, which means that the correct labels are classified in the needed accuracy, and also that the system parameters of all the physical nodes are met regarding resources. This task can be very time-consuming and is most probably not optimal when done manually. Within our approach, we are adding 2 system components in order to improve this scenario. The first is a machine learning model management component, and the second is a data stream management system. Those two components enable the automation and optimization of the manual steps. The very first step is still a manual step though, which is defining the requirements of the classification pipeline to be installed. The IoT engineer needs to specify the labels that should be classified in this pipeline. He needs to specify the accuracy thresholds, meaning the minimum accuracy for each label, and also the accuracy weight. The accuracy weight tells the system how important accuracy is in contrast to resource consumption. The last information that needs to be specified is the node information. That means which are the participating nodes where the classification pipeline processing should be distributed to, and also their resource limitations. First of all, within the machine learning model management component, the model set mining automatically retrieves models according to the defined requirements and combines them to model sets. The next step is the decomposition. That means that the classification pipeline of a model set or of selected model sets is decomposed and translated into data stream operator graphs. Those operator graphs, which means that there is an operator graph for each model, is now merged and redundancy within those operator graphs are removed, resulting into a single optimized reduced operator graph. This operator graph is now placed using operator placement to the distributed nodes in order to reduce resource consumption. And finally, the processing is deployed to the nodes. Using this approach, we are able to, on the one side, reduce the manual effort the IoT engineer needs to invest into setting up the classification pipeline, and also to reduce the resource utilization of the system. The model set mining component selects and combines models from the model database by fulfilling the requirements given as input to the model miner. The input is specifying the labels that should be classified by a model set in combination with the accuracy thresholds, which tell the minimum accuracy for a given label. Also, all the labels within a model set need to fulfill the model memory size constraints. That means that within those constraints, you can define the maximum memory size of a single model and also the maximum memory size of all models within a model set. Also, the accuracy query sharing weight is given as input. As told before, this accuracy query sharing weight is telling how important accuracy is in contrast to resource consumption. The last parameter is n. This simply is the number of model sets that should be returned. And the model set miner is returning the n highest ranked model sets regarding a scoring function. In order to score a model set, the formula on the bottom of the slide is used. As you can see, the average accuracy is used for the accuracy side, and a query sharing level is used on the resource side. The query sharing level works as follows. The values for the query sharing level is 0 to 4. Level 0 means that there is no sharing at all. That means that the classification pipelines of two models have no common processing. Level 1 means that the two models work on the same input data or sensor systems. Level 2 means that they have the same pre-processing. Level 3 means that they're using the same segmentation method. and level 4 means that they are using the same feature set. Also, those levels build upon each other. That means that level 4 can only be achieved when also level 3 is fulfilled, and so on. Within decomposition, the processing pipeline of classification is split into smaller tasks. We decided to go for the following 4 categories: pre-processing, segmentation, aggregation, and classification. Also, the processing pipeline is translated into an data stream operator graph. The implementation of the classification pipeline as data stream operator graph gives us the advantage of writing a classification pipeline as data stream query, which results in a higher abstraction level, so we do not need to write low-level code in order to implement the classification pipeline. Now getting to the redundancy elimination. As you have seen before, each model within a model set is decomposed to an operator graph. Within the redundancy elimination, all operator graphs within a model set are merged to a single operator graph by reducing redundant processing. On the left-hand side, you can see the input for the redundancy elimination component. There are 2 models within the model set, and the details of the processing pipelines are depicted there. The result of the redundancy elimination step is a single merged operator graph. And you can see here that only the pre-processing could be reduced by merging the 2 map operators in the pre-processing steps of the 2 models. This could be done because they are both using the magnitude function for pre-processing. No further redundancy elimination is possible here, since in the segmentation step they have different window sizes. Regarding terminology, we say that this model set provides full pre-processing alignment. That means that all models within this model set share the same pre-processing. In the second example, we simply say that the second model also has a window size of 5 seconds. Then you can see that also the segmentation step is merged within the resulting operator graph. So now the model set has full pre-processing and full window or segmentation alignment, leading to query sharing level 3. What you can also see here in addition is that the aggregate operators are merged, but they do not share a common aggregate function. This is because when 2 models share the same pre-processing and segmentation step, the aggregation step is always also merged. This is just a design. This may not lead to any reduced redundancy, but in case they share some common aggregation functions, it also leads to reduced redundancy. In example 3, we now assume that the second model in the model set also uses the min function in the aggregation step. In the result, you can see that now also the aggregation is fully aligned, which leads to a fully pre-processing window and aggregation aligned operator graph, which is query sharing level 4, the highest level of query sharing. The final optimization step of our approach is operator placement optimization. Within operator placement optimization, it is about finding the best valid mapping from operator graph to resource graph. The operator graph here is the redundancy eliminated graph from the step before, and the resource graph is the representation of the physical infrastructure with its limitations. Best in this concern means the least resource utilization. So the mapping that uses the least resources regarding our defined resource metrics. Our first metric is total network utilization, in bits per second. And our second resource utilization metric is memory consumption on edge nodes in bits. And a valid mapping is a mapping that fulfills all general constraints and all resource constraints. The general constraints are simply graph-related constraints, like that all operators needs to be assigned and that there are no multi-assignments, meaning that a single operator can only be assigned to one physical node, but not to several. And all edge directions need to comply also. The resource constraints simply tell that the physical limitations of the infrastructure is not exceeded. We have memory capacities of physical nodes and data rate capacities of communication channels between physical nodes. And those are not allowed to be exceeded in order to be a valid mapping. In order to evaluate our approach, we have implemented it prototypically and applied it to the previously depicted use case of kettle activity recognition. There we assume that farmer Alice wants to have a monitoring system for the cattle behavior of lying, grazing, and ruminating. For experimental setup, we assume a simple scenario consisting of 4 nodes, where there are 2 edge nodes, which are sensor systems attached to the collars assembled to cows, and 1 fog node at the farm and 1 cloud node. Each edge node sends data for 10 minutes with a frequency of 10 Hz. That means that each edge node is sending 6,000 tuples within our experimental setup, and that a total of 12,000 tuples are sent by the sensors. We also set up a model database containing about 20,000 models, which is used for our evaluation. The models have been created systematically. It appears that the model sizes regarding memory is from 700 bytes to 32 megabytes. And the accuracies of the models reaches from 5% to 97%. The evaluation metrics used in order to measure the performance of our approach are network utilization, response time, and latency. Network utilization was previously used as optimization criteria for the operator placement optimization. Response time is the time that our system needs in order to perform all the optimization steps, and latency simply is the processing and network latency of the classification pipelines. We have defined 5 different evaluation cases. The first case is the trivial baseline, which is cloud computing, meaning that all processing will take place on the cloud node and all the other nodes are just passing the data by. Also, within case 1, we are using manually selected models. So there is no optimization taking place in the machine learning model management nor in the data stream management system. As you can see in the shown operator graph, the 3 models only share common preprocessing. The second evaluation case is working with the very same manually selected models, but now we enable distributed computing, meaning that not all of the processing is taking place at the cloud node, but we optimize for operator placement and also use processing of edge and fog nodes. Evaluation case 2 can be considered as the second baseline evaluation case. This is not a trivial one because data is already distributed among the participating physical nodes. From evaluation case 3 and onwards, we are enabling the machine learning model management component model set minor. In evaluation case 3, we are setting the accuracy query sharing weight to 1, which means that only accuracy is important for model mining. As you can see in the shown operator graph, there is a partial window alignment between the models of lying and grazing. In evaluation case 4, we lower the accuracy query sharing weight to 0.7, which means that accuracy is less important and we want to aim for some query sharing in the model set. The resulting operator graph, as you can see, provides full pre-processing and full segmentation alignment. For evaluation case 5, we further lower the accuracy query sharing weight to 0.5. Now accuracy and query sharing is equally important for the model set miner. The resulting operator graph shows that we have full pre-processing, segmentation, and feature alignment. In the following, I will give a short summary about the performance metrics for our evaluation. First of all, we took a look at the network utilization of our system and evaluation cases. Regarding the baseline case in which all the sensor data is sent to the cloud, the operator placement optimization enabled a reduction in total network utilization from 80 to 98%. The operator placement optimization results have shown in cases 2 to 5 that performing pre-processing, segmentation, and aggregation on the sensor system on the edge is an excellent strategy to reduce network utilization. Cases 2 to 5 are all doing aggregation on the edge. But why does the network utilization decrease so hard? This is due to the smaller feature set returned by the model miner and also by redundancy elimination. Due to alignment, the processing and therefore also the data sent is reduced. A different aspect is the increasing window size from cases 2 to 5. As a second evaluation metric, we took a look at the response time of our system. You can see that in cases 1 and 2, the response time is quite small. This is due to the model set. There was only one manually selected model set, so the optimization task was quite easy. From cases 3 to 5, we had 3 model sets each. That's why the operator placement problem is more complex. But from case 3 to 5, the complexity of the problem is decreasing because of the increasing redundancy elimination. For case 5, there was a full alignment of pre-processing, segmentation, and features, so the number of nodes that needed to be placed were very small. Our proposed approach consists of 2 main components. The machine learning model management component, namely the model set miner, and the data stream management components, consisting of decomposition, redundancy elimination, and operator placement components. We have shown that our approach is able to reduce the manual effort needed for an IoT engineer in a real-world use case like activity recognition for cattle. The IoT engineer was assisted in selecting and combining machine learning models, in implementing the classification pipeline as data stream operator graph, and in operator placement and query deployment. Further, we have shown that our approach reduces the resource utilization, especially network utilization, regarding a trivial baseline case up to 98%, and for a distributed use case up to 94%. Thanks for your attention. we are now looking for answering your questions.